Okay, so continuing with our lab, the first task is to observe the operation of a buck converter. Okay, and as I mentioned before, the input and output voltage relationship of a buck converter is given by simply the duty cycle, where the duty cycle is T on divided by the period of the pulse. Okay, so this is the circuit that we're going to be using in PSpice. Okay, so let me go to the circuit and describe it. So I'm not going to show you how to build the circuit because you should be familiar with this by now. You should know the names of these components. So these are R, or the diodes, the inductors. Okay. Two few new components that we are using here are firstly the MOSFET, where the name of the MOSFET is given IRF840. You can search that and find it. We are also using a pulse generator, so V pulse. Okay, so this is the pulse generator, and we're using a voltage controlled voltage source here, and I'll explain why we're using that. So for the pulse generator, you will see that you have a few properties here, right? You have V1, V2, TD, TR, etc. V1 is the value of the low voltage, right? So the 0 means it has a low value of 0. V2 is the value of the high, or 12 volts. So we're basically getting a pulse that varies between 12 volts and 0 volts. TD is called the delay time delay. So we don't need a time delay, so we set it as 0. TR is the rise time. Okay, so if you want to have a pulse that has a certain rise time, okay, so if you add another rise time, it will not go straight up, right? It will take some time to rise to the final value. So we want the rise time to be as small as possible. So we put a value of 0.001 milliseconds. Similarly, TF is the fall time. Okay, so we set that as 0.001 millisecond, because if we set a higher value of fall time, it will take longer for the pulse to go from the maximum value to the minimum value, and then it won't be a square wave pulse. Okay, so it will just be a curved pulse. Okay, PW is the pulse width. Okay, so and PER is basically the time period of the pulse. Okay, so if the time period of the pulse is 0.2 millisecond, then if we have a pulse width of 0.1 millisecond, we are basically getting 50% right. So whatever value, so the maximum duty cycle we can get is obviously 100%. So that will be done with a pulse width of 0.2 millisecond, right? I hope you understand how that works. And now we also have a voltage controlled voltage source here. Okay, so to explain that, let me get back to the whiteboard. So we are connecting our pulses to our switching device, or the MOSFET, through a voltage controlled voltage source. And the reason we are basically doing that is because of the internal structure of the MOSFET. Okay, so we're not directly connecting the pulse to our switching device. If you look at so if we go quickly to your boost circuit, you'll see that it's directly connected to your MOSFET, the pulse. Okay, but due to the internal structure of the MOSFET, we are not able to connect the pulse directly to the MOSFET in the case of our buck converter. Okay, so as you know, the MOSFET has three terminals, right? We have a drain, a source, and a gate. And basically, when we bias the MOSFET, we bias it across the gate and the source. Okay, and the source is generally connected to the ground. Okay, so we have a bias voltage of plus minus. So the bias voltage across the gate and the source determines how the MOSFET operates, right? So in this circuit setup, we can see that if we have only the pulse generator, right? So we have a pulse generator going to the MOSFET. We don't have any opportunity to connect the source terminal to the ground, right? Because we want the bias voltage to appear across the gate and the source, right? So this is a gate terminal and this is a source terminal. If we use a voltage controlled voltage source here, we can generate another ground here, right? So we can put the pulse into one input and the ground into the other input. And if we do that, what happens is we can create a path for this node is basically then connected to the ground, right? So then we can get this, pulse voltage across the gate and source terminal of the MOSFET. That is the reason we're using a voltage controlled voltage source here. And you can find this by going to your component list and just writing E. Okay, write E and you can select E analog. that will give you your voltage controlled voltage source. See, this is the one. And the pulse generator is basically called V pulse, I think. Let me just check. Yep, it's called V pulse. So you can select the V pulse / source. Okay. And the MOSFET is, as I mentioned, IRF 840. Now, for the buck converter, if you remember, the ratio of the output to input voltage is basically controlled by the duty cycle. So in this case here, we have a pulse width of 0.1 millisecond and a pulse period of 0.2 millisecond. So the duty cycle is 0.1 divided by 0.2 or half. So in this case, for an input of 12 volt DC, we should be getting an output of 6 volts, right? So let's run the circuit and see what we get. Okay, so there is some fluctuation at the beginning because of our inductors and capacitors, but as you can see, eventually we reach a value of 6 volts, right? So with an input of 12 volts, we're getting an output of 6 volts using our buck converter. Okay, now if we change this value, so let's say we make it 0.05, then that is 25% of our input. Okay, so our input should then be around 3 volts, right? So let's run it. And as you can see, after some fluctuation at the beginning, we get close to a value of 3 volts. I think it's a bit larger than 3 volts, but that's okay. And if we increase the duty cycle, so let's say we make it 0.16, okay, milliseconds, so which is 80% of the which is giving 80% duty cycle, then we should get a value of, I think, close to 10 volts, I think. So let's run that. And yeah, I think it's supposed to be exactly 9.6 volts. So we're getting around 9.6 volts. So that's what we are expecting. So that's how the output of the buck converter changes with the change in duty cycle of the pulse, right? So this is the pulse that we're feeding to the MOSFET, remember, or the switching device. So we're using the pulses or the duty cycle of the pulses here to control our output. Okay, so that's the operation of the buck converter using your PSpice software. Now, as I said, we're going to be looking at both PSpice and Proteus software. So we're also going to study the buck converter using Proteus. And if you look at the Proteus circuit, it's a bit more complicated than our PSpice circuit. So in this Proteus circuit, we're going to be using the 555 timer pulse generator that I discussed already. Okay, so we're going to be using this to generate the pulses for our MOSFET. Okay, so let's go to Proteus. Okay, so this is the Proteus circuit of our buck converter. This whole circuit here is basically the 555 timer or pulse generator. Okay, and the output from this, so you can see that it's pin 3, right? The output of pin 3 we're basically going to be feeding into our MOSFET. Okay, so again, at the gate terminal of our MOSFET through a voltage controlled voltage source, because as I said, this gives us a ground that allows us to bias the MOSFET correctly. Okay. Now you will see that the pin at the output terminal is not directly connected to your MOSFET gate terminal, right? So we are using these triangular looking things, right? And similarly, we're using the triangles at the output to measure the output voltage too. Okay, so what are these? These are basically called your input and output terminals. So if you go to the right here and go to terminals mode, you'll see the input and output terminals. So wherever, so for example, say we're getting an output at pin 3, right? Then we can connect an output at pin 3. Right? If you double click on the, terminal label, you can change that label to say whatever you want, right? And in this case, we have it written as output. And then the benefit of this is then you can take an input terminal So for example, for the MOSFET, where we want to connect the output to the gate terminal, you can take an input in here, okay, place it here, then connect it to this terminal here. And then if you name the input terminal the same as your output terminal, so if you name this output as well, right, that basically means these two nodes are connected. So it will assume that this node here and this node here are the same. So we don't have to use extra wires. Okay? So we can just place an output terminal here and then connect an input terminal here. Make sure they have exactly the same name, so they're both called output. And then this output will show up over here. Similarly, you can also measure the output here as well. Okay. For example, I'm taking the output of the buck converter from here, right, the total output, and putting it into the oscilloscope through an input terminal. I'm also checking the value of the capacitor charging and discharging through an output terminal here, and we can view this at the oscilloscope using the same terminal or the input terminal here. Okay, but just keep in mind that they have to be exactly the same name. So output, and output here are exactly the same name. They also have to be same case. Otherwise, I don't think they will work. In terms of devices, all the device names are, I think, given in your lab sheet. So for the capacitor, in a lot of cases, we're using the normal capacitor. So this is generic capacitor. And we're also using this type of capacitor, which is called, you can see the name here, Gen Elect 470U6V3. Okay, so this is the capacitor that we're using here. And over here as well, I think. Yes. And the name of the MOSFET is IR3205. The voltage control voltage source is VCVS. Okay, and the diode is called 1N4007. So, and the 555 timer, you just write 555. So just come to the video at this point of the video, and you can pause it and see the name of the components here. Okay, and if you remember, I said that we can control the charging and discharging of the capacitor through these two potentiometers, and I'll be showing you that how the width of the pulses varies if we vary these two resistances. Okay, so let's run the circuit now and see what type of output we get. Okay, so if we run this circuit, and initially I think we're keeping it at both at 50%, so we're getting around fluctuating a bit, but I think it's around 9 or 8 volts. Okay, so the output. Okay, now let's look at our oscilloscope. Let's fix this a bit. Okay, so these are the capacitor charging and discharging. So as you can see, when it's charging, we're getting a high peak, and when it's discharging, we're getting a low peak. Okay. Now, if you remember, if we can control the charging and discharging through these two, right? So if we increase this, the charging time will increase. So the amount of time we have T on will increase, and if we increase this resistor, the discharging resistance will increase, so the amount of time it takes to discharge will increase, and hence the time that the output, the time of the low value of the output will increase. Okay, so first of all, let's make this. So initially, I think we're getting an output value of around 9 volts, right? So let's increase the duty cycle. So how do we increase the duty cycle? We will increase the resistance of the charging path. Okay, so we'll increase the resistance of the charging path to, say, let's give it 80%, and let's reduce the resistance of the discharging path. Let's reduce it to 30%. Okay, now if you look at your oscilloscope, you'll see that the pulses, when they're on, the width of the pulses have increased, and when they're off, the width of the pulses have decreased. So your duty cycle has increased, because duty cycle is the ratio of time on to the total time period, right? And if we look at our output, we'll see that it has also, oops, my Proteus has crashed. So be careful when using your Proteus, because I think this big circuit causes it to crash a few times. Okay, so as I was saying, when we keep our R1 to 65%, so we increase the resistance at R1, and we decrease the resistance at R2, then our duty cycle increases. Okay, so if you look at our oscilloscope, you'll see that the time on, okay, the on time of the pulse is greater than the off time of the pulses. Okay, and that means our output increases. Okay, so you can just wait for it a bit. You'll see that it will increase eventually. Okay, and the other thing is you can increase the resistance at R2. So if you increase that, and we decrease the resistance at R1, then the on time of the the pulses decreases and the off time increases, right? That means our duty cycle is decreasing, and the value of the output voltage will be lower, right? So you have to observe this in your probe case. It might be a bit tricky because this circuit keeps crashing, but try it and see what you find. Okay, so this is where we're using the 555 timer circuit. So for the other circuits, we're going to be using the pulse generator. So, but this is an interesting phenomenon where you can increase the resistances and decrease them and see the change in real time, right? So give it a try and see what you get. Okay, so next we have our boost converter, where the input-output relationship is like this, and basically the output voltage will be greater than the input voltage. Okay, so this is the circuit of our boost converter in PSpice. Okay, so let's go to PSpice, and you'll see that in this case we're connecting the pulse generator directly to our MOSFET, okay, to the gate terminal, because in this case the source terminal is directly connected to a ground. Okay, so the biasing voltage across the gate source will be appropriate in this case. We don't need to use a voltage controlled voltage source. So again, we can control the duty cycle by changing the value of the pulse width. So if our total pulse period is 0.2 millisecond, then a pulse width of 0.1 millisecond means we'll get 50% duty cycle, right? And if we have 50% duty cycle from here, if we put a value of 0.5 here, we will get a input-output ratio of 2. That means the output should be double of the input. Okay, so the input is 12 volts, so we should get an output of around 24 volts. So let's run that. And yeah, as you can see, the output is almost 24 volts. It's a bit lower, and as with before, we have a fluctuation initially. That's because of the capacitors and the inductors. So by using a duty cycle of 0.5, we can get around 2% increase. So, 2 times increase. So our output voltage will be 2 times the input voltage. Okay. And if you look at the equation, you'll see that the equation is such that if we increase the duty cycle, right, this ratio increases. So the voltage will be greater as we increase the duty cycle. Okay, the output voltage. So if we have a duty cycle of 80%, okay, so that will give us a output voltage that is around 5 times the input voltage. Okay, so let's put a value of 0.16 here. That will give us around 80% duty cycle. So we should get around 60 volts in the output. So yeah, we're getting close to 60 volts in the output, right? So that's the 80% duty cycle case. And if we decrease the duty cycle, right, if we make it, I think 25%, which is 0.05, we should be getting around around 16 volts, I think. Yeah. So let's run that. Yeah, around 16 volts. I think it's a bit less than 16 volts, but yeah, we're getting close to 16 volts. So this is when the output is decreasing as we decrease the duty cycle. Okay, so that's how the buck converter operates using using PSpice. And now we're going to be looking at the Proteus circuit. Okay, so this is a Proteus circuit, and let me go to Proteus. So this is the circuit of the boost converter in Proteus. So as you can see, we're not using the 555 timer circuit anymore. We're using this pulse generator. So to find this, you go to the right hand side here, you go to generator mode, and you select pulse. Okay, so this is the pulse generator, and you can tune the values of the pulse generator by double clicking it. Then you can see you can have your low voltage value, your high voltage value, and similar to PSpice, you have your rise time, you have your fall time, you have your pulse width, which you can change, and you have the frequency. Okay, so these are the values that are provided in your lab sheet. So just select those values initially. Okay, and the rest of the components we're using, the diode name is given, and we're just using regular capacitors and inductors, and our MOSFET is called RF840 as before. Okay, so if we have a pulse width of 50%, as I discussed before, we should be getting, if for an input of 12 volts, we should be getting approximately double the input, so around 24 volts. So if we run that, we can see that it's around 24 volts, a bit less. If we put a duty cycle of 80%, we should be getting, as we saw before, around 60 volts ideally, but it should be a bit less. Okay, so yeah, we're getting around 50 volts, 49. That's for 80% duty cycle. And if we have a duty cycle of 25%, as we saw before, we should be getting around 16 volts at the output, a bit less than 16 volts. So yeah, for 25% duty cycle, we're getting a bit less than 16 volts at the output. So you have to change the duty cycles like this and see what type of output you get for your lab report. Okay, so you can change the value of the pulse width and see what type of output you get. So that was the boost converter, and now let's move on to the buck boost converter. So for the buck boost converter, we have our input-output relationship like this, minus t divided by 1 minus t. So because of the negative sign, whatever output we get will be inverted. Okay, so keep that in mind. And this is the general outlook for PSpice. Okay, so we'll go to the circuit. And again, one thing you have to keep in mind is because the MOSFET is like this, so we need to use our voltage controlled voltage source to generate another ground, because we want the biasing of the MOSFET to be across the gate and source, right? So as I explained before. So this is the circuit in PSpice, and I think all of the components have already been described. And if you recall, for the buck boost converter, if we have 50% duty cycle as we have now, the output will be the same as the input. If we have greater than 50%, so if we have higher than 0.5 50% duty cycle, then it will operate as a boost converter, and for less than 50% duty cycle, it will operate as a buck converter. Okay, so let's keep it at 50% initially. So for the 12 volt input, we should be getting a 12 volt output. Okay, so let's run it. And yeah, the output is around minus 12 volts. So remember, it will be minus this time, right? Because it's an inverting converter. So we have minus 12 volt at the output. Okay, and if we increase the duty cycle to 80% duty cycle, so if we put 0.16 millisecond for the pulse width, we will get an output voltage of, I think, around 48 volts we should be getting. Okay, so let's run that. And yeah, so around 48 volts we're getting at the output, right? So now it's operating as a boost converter because the duty cycle is greater than 50%. And if we provide a duty cycle of less than 50%, so let's put it as 25% duty cycle, and then I think we should be getting around 4 volts or 33% of the output. And so we should be getting minus 4 volt at the output. Yeah, we're getting almost around minus 4 volt at the output. So now it's operating as a buck converter. Okay, so that's the circuit in PSpice. Okay, so let's move on to the Proteus circuit now. So this is the circuit of the buck boost converter in your Proteus. So as with the boost converter, we're going to be using the pulse generator instead of the 555 timer circuit, because that is actually a bit complicated, and as you saw, Proteus tends to crash when you use that big of a circuit. And it's a pretty simple circuit, I think. Let's go to Proteus. So basically we're using the pulse generator. As I showed you before, it can be found in the generator. The pulse generator can be found at the generator portion. Okay, so if you go to generator mode, then you can set pulse. And the rest of the components, the names are given, and I think we're just using generic capacitors, resistors, and inductors, so that should be easy for you to find. Okay, so in this case we're using 20 volts, and if we have a duty cycle of 50%, right, pulse width of 50%, we should get the around the same value of the input at the output, right? So let's run that and wait for it to go. Yeah, around 20.2 volts, so that is working well. And then if we increase the duty cycle greater than 50%, so if we make it 80%, it should operate as a boost converter, right? And the output voltage should be 4 times the input voltage, so we should get, we won't get 80 volts, but okay, but let's see what we get. So ideally we should be getting 80 volts. So let's make it 80% duty cycle, and we should get an increased value. So it'll work as a boost converter. So make sure you set the frequency to a high value, right? So we're using 70 kilohertz, so that should be given in a lab sheet. So for an pulse width of 80%, we should be getting 4 times the input, right? So that should be around 80 volts. We probably won't get 80 volts, but let's see what we get. So let it increase. 50 so far. Yeah, so we'll get around 50 volts, but yeah, it's operating as a a boost converter in this case. And then if we reduce the duty cycle to less than 50%, so if we make it 25% duty cycle, we should be getting around 20 by 3 or 6.67 volts, right? So around that. So if we want that, we'll see, yeah, we're getting around 6.7 volts, which is pretty close to the ideal value. So that's how the buck boost converter can be operated as a buck converter, a boost converter, or just a normal voltage buffer circuit, right? So I think that is the end of your lab. So, and now you just have to run all these circuits by yourself and provide the output values, okay, and attach that with your lab report, and you have to make a discussion. So see you all in the review class.